I can't just switch you out of the honors section like I used to be able to do. The honors program doesn't allow that, so you do have to follow through. Also, I do have your exams back for you today, so maybe a minute or two before class if I'm not in the middle of something. If not, then right after class ends, then I will get those back to you. And today we'll be starting physical optics, which is actually the beginning of your last homework. So this is homework 11, which will be due somewhere toward the end of the last week of class. So probably 3 days or so before the final exam. Okay, any logistical questions before we get to it? Okay, so physical optics is where we remember that light is a wave. So we've been doing, for homeworks numbers 9 and 10, geometrical optics. So geometrical optics is when you just have light as a wave, as a ray. So geometrical optics is when you don't actually have to do anything except track the direction of the light. You don't have to remember that there's actually something waving. An electromagnetic field is waving. Physical optics is where we return to the fact that there is actually a wave, because we're going to go back and we're going to revisit wave interference. The very stuff we were talking about in homeworks 3 and 4 with sound waves, waves on a string, we're going to go back and do them with light. So in some ways this is nice because it allows us to visit many of the ideas that we already learned. Constructive and destructive interference, phase shift, right? Phasers, right? All these things that we learned were useful things for waves. We're going to get a chance to go back over them and see them in a new context. So the first topic is something called two-slit interference. It's also sometimes known as Young's slit. So you'll see it by both names. So here's what we have. We have a barrier of some sort where there are 2 very narrow openings, or slits, and those are going to be where we can source our wave from, okay? Or our 2 waves from. So we've talked about point sources of light, or point sources of waves that look like this. We call these wave fronts. They're marking off what the crests are doing. And we can, of course, add rays as well, so on and so forth. And I should point out that ... way over here, where essentially the waves have gotten spread out spherically to a large enough area that you can't tell that they're curved anymore, right? If the circle gets big enough, it looks locally flat, just like the Earth, right? So far away, essentially, the wave fronts have gotten parallel to each other, and the rays have essentially are approximately parallel. We're so far away that we're essentially looking at a locally flat section of this wave. So that's what we're going to shoot into these 2 slits. Here we go. Make sure it's wide enough. And what you notice, of course, is that the barrier is going to block most of the light. Only if you've shot right down in the right spot, right about here, let's say, are you going to actually get through. So what we have are 2 waves that will emerge from the slits, and they are in sync or in phase, because, of course, they were sourced from the same original wave. So when a crest of this one arrives, a crest of this one will arrive. Okay? So we have 2 waves that are in phase that emerge. Now, before you think we're just going to have kind of 2 waves that go straight, it turns out that it's a little more complicated than that. So it turns out that once the waves arrive at the slits, the part of the wave that is getting through is going to have a chance to spread out again. In fact, it looks like this. So there's a couple different ways I can try to motivate that. One of the ways you can motivate it is something called Huygens principle, which I'll just mention briefly. It's a general principle about all waves, light included, and it basically says this, is that every point on a wave is ready to become a new source, okay? So if you have, say, a point on a wave like this, that is ready to become its own source of spherical waves. So over here, all of these points are ready to become their own source of spherical waves, and in fact, it's the net sum of their motion that perpetuates the wave going forward. So over here, they shoot waves at each other, those just cancel, but in the forward direction they all agree. So any wave can be thought of as just a bunch of points, each of which are ready, willing, and able to become their own source of spherical waves. Okay? So when these two guys are left alone, they will do just that. Okay? When everything else gets blocked, except for what makes it through those narrow slits, they themselves become their own source of spherical waves. So here's the analogy that I like to use. If you don't like that, think of every point on the wave like this. Think of it as a bunch of soldiers marching shoulder to shoulder. You've seen the old Revolutionary War days, right, where the soldiers all just kind of go like this and they all stand next to each other. So you're nice and cramped. You got somebody right here, you got somebody right here, and then suddenly they get shot, okay? Now you're by yourself, you might as well spread out a little, okay? So that's what happens here. The adjacent parts of the wave, it's blocked, and only one part of the wave makes it through, so it takes the opportunity to spread out again. So we are now in a situation where we clearly will have some interference. You can see there are parts right here where the two crests coincide. That will be a constructive interference. And let me try to find a spot. Let me not be stingy here with colors. Let me grab another pen. So let me suppose, for instance, that I'm marking off the crests with a solid line, and halfway between I'll mark off the troughs, of course. So I might mark over here, halfway between this crest, these two crests, I'd mark off a trough. And I want to point out here that right here, the trough of that wave encounters the crest of the other. So when crest and trough meet, what happens?
Destructive.
You get destructive. Now, you could do this all day. You could find spots in this whole mixture where the two crests line up, and other spots where the crest and the trough line up. So rather than worrying about the entire volume in this space, I'm going to restrict my interest to an observation screen over here. So I'm just going to ask what it is that I see there. That's where I'm going to actually observe the light. Okay? So, let's go ahead and think about this. One of the things I want to do first is to, instead of drawing it with the wavefront picture, let me just flip it so that I'm actually drawing the wiggling of the waves. So before I was drawing this, crest, 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 and trough, trough. But let me just draw that familiar sinusoidal pattern. So let me draw it again right here. So, let's start with the center of the screen. So the center of the screen is the spot, by definition, that's equidistant from both slits. So I might draw that, I go like this. So what kind of interference do you think you're going to get right at the center of the screen? Constructive or destructive?
Constructive.
Constructive. They're in sync over here. They're in phase. They're the same wavelength.
Same distance away.
And they travel exactly the same distance and arrive at the center of the screen, so how would they develop any out of syncness, right? you're going to get a constructive at the center of the screen. So the question then is, what about other points? Okay? So maybe you can already see where I'm going with this. They're going to be able to have constructive or destructive interference, not because they aren't the same wavelength, they are, not because they aren't in sync at the slits, they are, but they have slightly different transit distances, right? One will travel slightly longer than the other to get to a given point. So let's work that out. What if we're over here somewhere? What do we see? So what I have to do is I have to measure, if I label this slit 1 and I label this slit 2, I would have to measure how far it is from slit 1 to that point on the screen of interest. I'll call that L1. I'm using lowercase script l because there's going to be another use for capital L in a second. And I also have to measure the distance from slit 2 to that point. So that's L2. And so I can, of course, well, I guess I can draw it. It's going to look ugly, but I'll go ahead and draw it. If you don't have to, if you don't want to. Here's the wave coming from one. Here's the wave coming from the other. So the question is, what are we going to see? Well, the interesting quantity here is path difference. It's called the path difference. So it's just the difference in travel length to get to that point on the screen. It's going to be slightly different depending on which slit you're coming from. So here's where I will appeal to your previous intuition about waves. So what if the two waves travel different distances, but one travels exactly one wavelength longer? What happens when you offset two waves by one wavelength? What kind of interference is that?
Destructive?
It's constructive. If you offset by a full wavelength, that's like no offset at all, right?
Yeah, exactly.
What if they're offset by two wavelengths, three wavelengths?
Still
Then
the
same thing, right? So as long as the path difference is an integer number of wavelengths, you're going to get constructive interference, right? So I'm going to write it like this. M times lambda, where m is any integer. And that will be my condition for constructive interference. Okay? What if the path difference is a half a wavelength?
Cancel each other.
They would cancel now, right? You shift a crest onto a trough. Yes? What about if it was 1.5 wavelengths, or 2.5 wavelengths, or 3.5 wavelengths? Well, if we're talking about 3.5 wavelengths to 3 wavelengths, you're back to square one, but the half is the killer, right? So the way I'm going to write this for destructive interference is I'm going to use the same index integer, and then I'm throwing an extra half, which is really what makes it destructive instead. Okay? So those are your conditions for constructive and destructive interference. Does that make sense? Question?
So what are we talking about when we're talking about screen? Are we talking about a TV or anything, or an eye?
It literally is just flat wall.
Okay, okay.
I mean, we're watching, letting the waves hit it, but we're only looking at the waves that hit the wall. So the only other thing that I want to do to modify this is to point out that it is nice when you always do the subtraction order in a certain way. So let's say I always do L2 minus L1. Now that works fine above the center of the screen where L2 is the longer one. Okay? So when you're above the center of the screen, you'll always have to travel longer from slit 2. So that means delta L is positive. But if I'm on the other side of the center of the screen, of course I'd have to travel longer from slit 1 now, and I have a shorter distance from slit 2. So instead of just reversing the subtraction order, I'm going to allow for the fact that delta L is negative. So delta L is positive on one side of the screen and negative on the other. Now, if delta L is negative, obviously my wavelength can't be negative. So I'm just going to allow negative integers for m as well. So these can be any integer including negative. In fact, over here, I'm going to have my positive integers, and here I'm going to have my negative integers. Okay? It's just a cataloging system. The m's are just are basically going to be counting the different things that I see. Okay? So let me go ahead, I guess, and show you what happens here. I have this very set up right here. So this is basically what I have on the board. I have two waves coming out in sync. I've put the crests as red dots, and I put the troughs as black dots. Here, this broke off, so you can't see it, but this is red and this is red, so a crest is emerging out of both. Okay? So, over here, I can see that at the center of the screen, you can see that red lines up with red, right? So that right there is the center of the screen. Let's keep going. I'll use this as my observation screen. I shift up a little bit. Now what you should see is red and black line up, right? So that's my constructive, or sorry, my destructive, right? They're off by half a wavelength. I have to hide the extra half wavelength behind here because I can't make these meter sticks shorter, right? So immediately to the side of the center of the screen, you will get a destructive interference, right? So let's keep going. We go up here. So now we have that red lines up with red again. So we get a constructive. Now they're offset by a full wavelength. So hopefully you see where I'm going with this. They're just going to alternate, right? As you go away from the center of the screen, the path difference is going to be a half wavelength and a full wavelength, a wavelength and a half, two wavelengths, so on and so forth. It's going to look like this. Constructive, destructive, constructive, destructive. Same thing over here. They just alternate. Does that make sense? Yeah.
Doesn't that mean that the wave that is going to travel longer is going to have less intensity? And
yes, it does. We're actually going to neglect that in this phenomenon because it's going to throw an extra thing we have to worry about into it. So one of the things we actually won't worry about is the drop in intensity as you get further away. I should mention, by the way, that not only is that going to be a problem for the intensity decreasing, but it also means that unless you're at the center of the screen, they always have different intensities from each other, which is a whole extra mess we don't want to deal with either. Now it turns out we don't really need to care because, for reasons that I'll get into later, we don't really look really far away from the center of the screen anyway. There are reasons why we might want to keep our region of interest close to the center of the screen where not a whole lot changes, okay? So that's my general condition, and this right here, in and of itself, you can actually work with this. The only thing that makes it kind of annoying, and so you will find, I think, a homework problem or two where you have to actually do the geometry to figure out how far is L1, how far is L2, what's their difference, and go over here. Notice that if I went to all the trouble to find these two lengths and then I went to a different point, I might have to do the geometry all over again. Okay? So delta L is generally calculated by geometry, and it oftentimes can be a case-by-case basis depending on the exact situation. Now that's something we do not want to get into if we can avoid it. So what I'm about to do is make two approximations that are very good for light, not necessarily other kinds of waves, but for light, that not only are going to make the math a lot easier to work with, but also are going to be perfectly valid for seeing the pattern anyway. So our whole goal with this is to be able to see this pattern for visible light without any specialized equipment, just with the naked eye. Okay? So we don't care about this pattern necessarily for, say, radio waves, or we don't care about it for visible light that's so dim that we can't even tell. We are very specifically interested in the special case of visible light that you can see with the naked eye, and for that reason, one might as well make some approximations that are true in that case. Okay? So let's go ahead and start with that. So this is approximation number 1 of 2 total. You may notice a running theme throughout this course is that we make approximations to make progress. That's something that you do in physics and engineering that you don't do in math class often. Okay? It's a toolkit you need to have, whether it be small angle approximation for pendulum, or the hot or close approximations for radiation law. These are just common themes in how you approach solving problems. So in this case, why do I make this approximation? I want to be able to see the pattern with no special instrumentation, the naked eye. Okay? So it has to be visible light that I'm working with in the first place, and it has to be bright enough. Okay. So, what is the approximation? Well, my approximation, and you're going to see why this is necessary to see the pattern with the naked eye, I have to add 2 more things to my diagram. I'm going to add capital L, which is the total slit to screen distance. And I'm going to add D, which is the slit separation. Okay? So my approximation is going to be L is much, much greater than D. So the distance from the slits to the screen is going to be far greater than the slit separation. This ratio can be on the order of 1,000,000 to 1. In fact, this might be a good time to show you the pattern in actuality. So let me shine it on the back wall here. So, oh, don't want to shoot you in the eye. Okay. So there is just a green laser beam in and of itself. That's the raw light. And I'm going to shine it through a double slit. And let's see if we can get that bright, dark, bright, dark. There we see it. You see the dots? Bright, dark, bright, dark, bright, dark. Nice, thank you. Okay. So first of all, L here, the slit to screen, this thing here, that's the length of our classroom. That's many, many meters. Okay? The slit separation, these are separated by about the width of a human hair. Okay? If that. They're tiny. Okay? They're tiny, tiny separation. So hopefully you believe me that this is indeed an approximation that is, at least in that case I just showed you, is definitely the case, right?
I believe you.
Okay, so that literally might be 1,000,000 times further from here to the back of the classroom than between these 2 slits. Okay, so that, if I try to draw this to scale, although drawing something 1,000,000 to 1 to scale is almost impossible, let me try. If I were to draw this to scale, it looks like this. So there's 2 slits, which unless you're in the front row, you can't even tell I just used 2 slits. And then way over here is the screen, okay? So this is L, and then there's a tiny little slit separation, okay? That's D. So let me attempt to draw this, and I'll attempt to draw the two waves. I'm not going to do the wavy part, I'm just going to draw the path. Oh, it looked okay until the end. I kind of lost the thread. But so basically you have two light beams coming from almost the same place, traveling a very long ways to interfere, okay? That basically means that these two beams are approximately parallel. Now, of course, they can't be truly parallel because otherwise they could never meet, right? They come from different places, and if they were traveling parallel, they could never meet to interfere. So I'm not saying they're exactly parallel, I'm saying they're almost parallel. They might go out with a tiny, tiny little bit of difference, right? If you and your friend, both exit, two adjacent doors, and then you meet later, 50 miles away, you basically travel the same, right? So I'm going to actually approximate that both of these went out at about the same angle. Right? That is what this approximation gets me, that the light is approximately parallel. Does that make sense? Okay, so what math shortcut will that get me? If I'm going to make that assumption, how will that allow me to do something easier and quicker than if I were trying to do the incredibly most general thing that is possible? So what I'm going to do is I'm going to zoom in, super mega zoomed in view of what's going on here. I'm going to zoom in here, and let me draw it down over here. So now, of course, I have to draw the slits much further apart because I'm zoomed in like crazy. And I'm going to draw the two light beams going out basically parallel. So this one goes out at approximately angle theta, and this one goes out at approximately angle theta. So they're basically approximately parallel. It's only much, much further on over here that they eventually meet and interfere. So they very, very, very slowly come together and eventually interfere at the screen, but as far as we're concerned, it looks like they're basically coming out parallel, right? So, what can I do with this? Well, it makes it very easy to compute the path difference. Rather than a case-by-case, I'll just do it once and for all. Here's what let me do this. Let me drop in a perpendicular. And I'll put a dot here on both ends of that. So I dropped a perpendicular like so from the top slit all the way to somewhere on the bottom beam. So why did I do that? Well, here's what happened. If the waves are in sync at these two dots, they will stay in sync all the way on down. So if I have, for instance, a crest coming out of the slit at this point, and I have a crest right here, they're still going to sync up all the way over here, right? So it's still going to be crest and crest down here, or crest and crest over here, and crest and crest and crest and crest until they meet and constructively interfere, right? So essentially what this allows me to do is realize that this extra little stretch is really the only difference in length. It allows me to approximate the difference in transit length as all being right there. This is my delta L. So let me try it here with my setup. So the first thing I have to do to modify this is, of course, to somehow make sure that these are going out parallel. So now I'm doing a super mega zoomed in view of what's coming out of the slits. So this allows me to hold them basically parallel, right? So way, 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 way over there somewhere, a million times further away than this slit separation, they will meet, but it allows me to examine what happens. So I'm going to drop in this thing right here. This is kind of going to act as my perpendicular that I just dropped. If I can get it in here, and I can't because this needs to get raised up. Okay, so basically this allows me to drop in a perpendicular, right? Like this. See that? So you can see, essentially, as it says here, if you can read it close enough, it says path difference is here. So it points to the extra little bit that this wave has to travel, okay? So for instance, right here, notice that I have an extra little bit here. Oh, what's going on here? Stay on there.
Please.
Okay. So right here you can see I have the red dot here to indicate a crest is coming out of this one, and there's a red dot here. But now what you can see is that the red and the black line up, right? This has traveled an extra little bit, right?
Okay.
So crest to trough, right? And so if they have the relationship of crest to trough right here, they'll have it all the way down there. Here's a case right here where there's an extra little bit.
Crest and crest.
Now it's crest and crest from here on down the line. So we can characterize the extra little bit of length as all being right here. Does that make sense? Okay. So it makes it so that you don't have to do the path difference case by case. Let's in fact work out the geometry once and for all. So if this angle right here is theta, then this right here will be 90 minus theta, right? And then this is a right triangle, this will be theta again. And then this again is d. So there's a right triangle in there whose hypotenuse is d and whose opposite side is delta L, so we can say that sine of theta is equal to delta L over d. Well, hey, that's great, because we've just figured out a quick way to approximate the path difference for everywhere we want on the screen. Here's our math shortcut. Delta L is approximately equal to d sine theta. Does that make sense? Okay, so let me show you where this gets you. We can very quickly come up with extremely useful formulas where we plug in d sine theta for the path difference. So let's rewrite the constructive equation. The constructive equation, let me throw the d on the other side, looks like this, and the destructive equation looks like this. Now, this may not look like much, but really, let me add in c and d subscripts. What we now have is an angular map of where we can find all of this stuff. So we have a map of angular location, okay? You can generate a bunch of angles where the constructives can be found. Just run through your various m values, right? You know what wavelength, let's say, you're working with. You know your slit separation. Just run through all the different integers, and it'll give you a bunch of different angles where you can find the constructives, the bright spots. you can run all your m's through this one and get a whole series of angles that you get the destructive spots. Okay? So now we have an angular map of the constructive and destructive locations. This is in terms of angular location, where theta equals 0 is the center of the screen. That's your reference. And then these are the various angles from there that you will find these various features. Does that make sense? So that's step 1. The first approximation is done, and I guess I should tell you, why is it necessary for this to be true, to see the pattern with the naked eye? I'll give you a little bit of a preview of that. The pattern needs to be spread enough, so I'll say enough spread to see it. So we found, if this wasn't true, if L wasn't much greater than D, you would still have a pattern, but it would be too smushed to see it. If there isn't enough of a gap between the bright spots, you can't see the dark one in between. Okay? So I'll show you what that's all about, but I want to do the second approximation first. If we're going to see this like I just did on the back wall, the brights have to be far enough apart to resolve them, and it turns out that this is necessary for that. Okay? But before I get into that, why this approximation makes it easy to see with the naked eye, I do want to do one more thing. This is my approximation number 2 of 2 total. So do think through these approximations, why they make sense, and especially on the homework, you may not always be able to make them. The second approximation is what allows us to go from angular location, which is kind of a weird way to do it, to actual physical location. So we might want to throw a y-axis on here, with y equals 0 as the center of the screen. So the center of the screen is not only theta equals 0, it's y equals 0. And the second approximation is going to allow me to convert from where do I see these things angularly to, okay, how many meters from the center of the screen do I see it? Okay? So, why do we make, so what's the approximation? Why do we make it? It's the same reason. Same reason as before. We are making approximations that are valid for being able to see the pattern with the naked eye for visible light. And what is the approximation? The approximation is a small angle approximation. So, we've talked about this before with a pendulum, right? Now, you saw that pattern that I projected on the wall. Those angles seem pretty small, right? How much was the total angular width of that whole thing? Maybe a couple degrees total? It didn't go from wall to wall, did it? A couple degrees. Now, why is it that it disappears? Why don't we get it all across the thing? That is yet to be addressed, but certainly you might see, hey, that was only a couple degrees width, right? Okay? So I should mention, again, the reason is that something called single slit effects make the pattern too dim to see at larger angles. So again, I'll talk later about what the heck that means, what's a single slit effect. But the point being is that if we just empirically, just by shining it on the wall, we can't see it for larger angles. Let's just go ahead and assume our angles are relatively small, and we can make whatever mathematical shortcut would be available there. So what's the math shortcut that we can have if the angles are small? Well, here's what it is. This right here is a right triangle, basically. And this side is y, and this side is L. So tangent of theta is equal to y over L. So there's my connection between theta and y, right? That's what I'm looking for. The only issue, of course, is that this is a tangent, and this is a sine, but if we have a small angle approximation, then we actually don't have to care. The first term of the Taylor series expansion for both sine and tan is theta, which means that we can do something that might be considered totally blasphemous in math class, which is we can set a sine equal to a tangent, and don't look back, okay? So that's exactly what we're going to do. We're basically going to say, tangent, sine, who cares, okay? And we're just going to plug in theta equals y over L. Y over L. And then we are done. Let me solve for the constructive and destructive conditions when both of our approximations have been complete. And I should label them as well. Hold on 1 second. These are the y values of the constructive. These are the destructive. So what we have now is the full capability of making a map of the brightness. Where are the features in just terms of physical distance along the screen? So those brights, darks, right? So bright, dark, like that, okay? Let's draw it. Only thing I'm going to do is I'm going to flip the axes a little bit to the traditional way that you present things. I'm going to put the independent variable on the horizontal axis. So that, ironically, here is y, right? We're walking along y. We're taking a stroll along the screen. And then the dependent variable goes on the vertical axis. That's the intensity we would see. Okay? So let's go ahead and draw it. It's going to look something like this. So there are spots where the waves are going to line up completely. These are the constructives. There are spots that are going to totally go to zero intensity. Those are the destructives. And you guys probably remember from our earlier discussion, it isn't just on, off. There's totally constructive, and then there's offset a little bit, and then there's offset more, and then there's totally kill each other. So this isn't like digital 0, 1, 0, 1, 0. It is a curve. And in fact, next time, Monday when we return, we'll derive the exact shape of that curve. Right now we're just finding the maximum and minimum. So let's try it. Let's just start running through the m values. M equals 0 will produce y equals 0. So we get a constructive in the middle, which we already knew. So this is the m equals 0 constructive, y equals 0. Then we put in m equals plus 1, and that will give us plus lambda L over d. Okay? Then we put in a plus 2. This is the m equals plus 2. that's plus 2 lambda L over D. We can try some of the negative ones. M equals -1. That would be minus lambda L over D, so on and so forth. So we've effectively used the constructive Y formula to find a couple representative places where it's constructive. All right? Let's try out the destructive one. So if I plug in M equals 0 here, I get 1/2 lambda L over D. So this is my M equals 0. Let me get a decent thing here of a different color. So this is my M equals 0 dark. That's plus 1/2 lambda L over D. Let's try plugging in M equals -1. So -1 plus 1/2, that's -1/2. So this is the M equals -1. That's minus 1/2 lambda L over D. Now you may find this odd that the M values look so asymmetric, but note that the Y values are not, right? The Y values that are produced are totally symmetric. Nature doesn't really care about the cataloging of which M value is which Y value. It just has to display all the things at the locations that we have shown. In fact, I should note that in some books they have this as a minus. That's totally fine. If two waves are offset by a whole number of wavelengths minus 1/2, well, that's still the same thing, right? The only thing that changes is how the M values are cataloged. It changes it so this is the M equals 0 instead of this one. But the actual Y values produced by both formulas still are the same. And that's the important part, right? And we can keep going with this. This is the M equals +1 by my cataloging system. That's 3/2 lambda L over D. And this, as you might guess, is the minus of that. Minus 3 lambda halves lambda L over D. So there we have a full map. And I should point out that what's perhaps more important than knowing exactly which M value is cataloged as what is the general spacing. Look at the spacing. So the delta Y between any two adjacent like spots, so that's a constructive and the next constructive over, or destructive and the next destructive over, is actually a fixed interval. These alternate like clockwork. And so I'll actually quantify this as the spread of the pattern, because it generally tells me about the spacing. So how narrowly or how widely spaced is the pattern as a whole? Because if you know any two adjacent like spots are spaced by that, that sets the pattern for the whole thing. Sets the spacing for the whole thing. Okay, so let me knock off there for today and get you back your exams. That's a good spot. I'll try